Hello students, this is Mr. Ferris. I'm going to walk you through lesson 13.1, the first lesson of the last chapter we have to cover. This should not be any harder than anything we've done so far this semester. First of all, I'd like to go over the answers to the quiz you were supposed to take before this lesson. The first one is just powers of 2, so the next one would be 64. The second one is multiples of 3, so the next one's 18. This one is the digits of pi, so the next one is 2, if you happen to remember that. Number 4 are the prime numbers, so the next one would be 13. Number 5 is a very famous sequence of numbers that you may or may not have heard of, called the Fibonacci sequence. And its pattern is you get the next one by adding the two previous numbers. And so 8 plus 13 would be 21. Number 6 is a little out there. These are the digits of our school phone number, the main, if you call the main office. So 680, I think 0 was the number you were asked for on the quiz. Number 7 is also unusual. These are the first positive integers, but they're spelled, and this is the first letter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think T was the one you were looking for in the quiz. Number 8 are those same digits, but they are arranged in alphabetical order. So 8, 5, 4, 9, 1, 7. Those are alphabetical up to this point, and so the next one alphabetically would be 6. Number 9 should be familiar because you hear this sequence every day at school. These are the first letters of the words of the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America. I think A was the letter you were looking for on the quiz. And the last one, this is mathematical again. This is an exponential decay, and each number is 2/3 of the previous number. And so if you follow that pattern, you should get 48. So these are some examples of sequences of numbers of sorts, even though some of them were letters. But now we get down to the definition. Our definition that we're going to work with is a sequence is any ordered set of numbers. So right there, that's going to eliminate maybe one of these or two of these from being technically a sequence by our definition. So number 7 definitely is not a sequence because that's letters. Number 9 is not a sequence. The other ones, though, I think are really technically all some sort of an ordered number, even if it's a telephone number or if it's alphabetical order. If they are numbers and they're ordered in some way, then technically, yes, they are a sequence. The individual numbers are called the terms. A sequence can be finite or infinite. There are both kinds. Finite end at a certain number, and then infinite ones would go on forever and ever. We denote the terms of the sequence by subscripts, and we use the lowercase a. That's the conventional. So the first term of any sequence will be a subscript 1, and that would be followed by a subscript 2, a subscript 3, a sub 4, etc., etc. And then when you get to the last one, if there is one, it would be a sub n. If it just keeps going, a sub n stands for the general term. So a sub 1 is always the first term. A sub 2 is always the second term, etc. And then a sub n has two uses. Sometimes it's the actual nth term. Maybe you're trying to find the 26th or the 28th. Or you could just say, well, the nth term is the general pattern. And so sometimes you're asked to find the nth term in a formula. And if there's a pattern, then we should be able to find mathematically a formula for how do you get a sub n. And we'll be doing that a lot in this section, in this chapter. So for instance, if they gave you a formula for a sub n, and they said it was 1 plus the square root of n, and we wanted to find the first 3 terms, we just have to plug in 1, 2, and 3. So if you plug in 1, the first term is 1 plus the square root of 1. The second term is 1 plus the square root of 2, and the third term is 1 plus the square root of 3. Nothing too terribly difficult about that. The 98th term then is not that hard either. We can skip right to it because all we have to do is plug in 98 for n, and that would be the final answer. The only thing we might do is that first term is actually 2. We could simplify that, but that is the pattern. And then part B, we're trying to find the first 3 terms. So again, you plug in 1, you plug in 2, you plug in 3. Now you got to be careful because this is interesting. You've got a negative 1 to the nth power. So when you plug in 1, that will be negative 1 to the first, which is a negative. And so that will be, I just noticed there's a typo here. This should be a multiplication, not a plus sign. So make that change. So the first one is going to be basically a negative sign in front of 1 over 2. If you plug in 1 for n, you'll get 1 for the numerator, and you'll get 1 plus 1 for the denominator. But the sign out front is going to be the odd power of negative 1, which is a negative number. Notice when n is 2, now we've got 2 powers of negative 1, and 2 powers of negative 1 is actually a positive 1. So we will just get the positive value of 2 over 3 when you plug in n for the numerator and the denominator. And then the next one is going to be an odd power of negative 1 to start with, so you have a negative sign in front, and then you have 3 over 4. So what's interesting about this little piece in front is that's how you get alternating signs. If you need a sequence to have alternating signs, then you simply put negative 1 to the nth power. Just make sure that when n is odd, you want the negative. When n is even, you'll get the positive. And so when you get to the 98th power of negative 1 is positive 1. So we really don't have to worry about that. And just plug in 98 for n, and that'll give you 98 99ths. That will be the 98th term. So far, so good. We can do the same thing for something that's a little more complicated by plugging in the first 5 numbers for n. So when you plug in 1, it would be 500 minus 10 times 1, which is 490. When you plug in 2 for x, that'll be 2 tens subtracted from 500, so that'll give you 480. And maybe by now you can kind of see, oh, I see what's happening. We're going to go down 10 every time. That's really the pattern. We're going down 10 every time, 10 every time, 10 every time. And so after a while, you don't need to just calculate, you just continue the pattern. In fact, you might notice that this particular sequence has a linear pattern to it. This is a sequence called arithmetic. Notice it's spelled like arithmetic, but you pronounce it differently. So this is an arithmetic sequence, and by definition, an arithmetic sequence is a sequence with a fixed, or if that word is unfamiliar, fixed just means constant. A sequence with a fixed or a constant difference between pairs of consecutive terms. That common difference in example 3 is negative 10. The numbers are going down by 10 every single time. So you look at any pair of 10, the one on the right will be 10 less than the one on the left. Any sequence that has that pattern is arithmetic. So looking at the next 4, which ones are arithmetic, all you have to do is just see if the numbers are changing by the same difference every single time. And it looks like, if you go left to right, this would be, yes, it's arithmetic because there's a common difference. And in this particular example, the common difference would be negative 4. It goes down 4, down 4, down 4, down 4 between pairs of consecutive terms. Number 2, we're going up 3, we're going up 6, up 12, up 24. So no, that's not arithmetic because there is no common difference. You have different differences, and that is not arithmetic. On this next one is a little more algebraic. Between the first term and the second term is p higher. The third term is p higher than the second term, and the fourth term is p higher than the third term. So yeah, technically this is a arithmetic. The common difference is whatever p happens to be. We're assuming p is a number. It could be negative, it could be positive, but as long as it's a number, that would be arithmetic. And D, if you look at 10 to 5, that's going down 5, 5 to 0, down 5. This looks arithmetic until we get to here, and all of a sudden it changes to add 5 and add 5. So that's actually not, you have to have exactly the same common difference. So this one would be no, because there is no common difference. It changes from -5 to +5. All right, so now we've got a formula to develop here. If we look at this sequence, it's fairly simple, so we can see kind of the pattern. The first term, obviously, is 2. The second term is 6, but you know, we could write that as the first term plus 4. Because if you'll notice, these terms do go up by 4, up by 4, up by 4, up by 4. Therefore, it's arithmetic, and so we can start to see a pattern that will lead to a formula. The third term is 10, which again, if we write it as the first term plus some 4s, you realize that, oh, well, 10 is really just 2 4s higher than 2, which is the first term. And if you go back 1, this was just 1 4 higher than 2. And so if you analyze each term, you find out you can always write an arithmetic term as the first term plus a certain number of differences. That common difference that we would have written down is plus 4, plus 4, plus 4, plus 4. So if the common difference is 4, we see that we can make a formula out of this. There's a definite pattern algebraically. So if we write it algebraically, you'll notice that we have added some copies of 4, which is our common difference. So how many 4s have we added? Well, to get the second term, we added 1 4. To get the third term, we added 2 4s. To get the fourth term, we added 3 4s. So you'll notice we always added n-1 copies of D. So that makes our formula turn out to be any term that we would want to figure out. We don't have to start at the beginning and go all the way to the end. We can just use this formula because we know from this pattern, every term in this sequence is the first term plus n-1 common differences. And that's useful if you want to just jump to the 50th term or the 60th term. You can just plug that into the formula and you can jump right to that term. You don't have to write them all out. So just summarizing again, to find the nth term sequence formula is the first term plus n-1 times whatever the common difference is. And A1, of course, is the first term. You always have to know that. You have to know where you're starting. And then D is the common difference between consecutive terms. So for an example, if we wanted to use this formula, what if we bought a car that had 15,000 miles on it when we purchased it, and let's presume that we drive it 8,000 miles per year. That could form an arithmetic sequence. And so if we write the formula for this thing according to the rule that we discovered, the nth term is always going to be the first term, which was 15,000 miles, plus n-1 times the amount of miles we put on it every year, the difference, which would be 8,000 miles. So that would be our formula for this problem. We just substitute A1 and 8,000 in for the two constants in our formula. So now, what if we wanted to find out after 7 years after we bought this car, how many miles would it have it? Now, it says to be careful here, because what you might notice if we write out some terms here, let's just write out a few. So the first term, when n is 1, the first term is 15,000, that's what we started with. The second term is 15,000 plus the 8,000 miles, so that's 23,000. The third term would be 16,000 more than when we bought it, so 31,000. And what you'll notice is after 1 year of having this car, we are now on the second term. So that's where it gets a little confusing. After 1 year, we get term 2. After 2 years of driving this car, we're at term 3. So if we want, after the 7th year, if this is year number 7, then we're going to be searching for the 8th term in the sequence. So you have to pay attention to the sequence number versus the time that's passed. So actually what we're going to do is we're going to use our formula, but we're going to plug in 8. So for our nth term formula, it's going to be 15,000 plus 8 minus 1 times 8,000 miles. And that'll give us 15,000 plus 54,000 miles, which is 71,000 miles. That will be the final answer. It's after 7 years of owning it, but it's actually the 8th term in this sequence. All right, that's arithmetic sequences, but there's another kind of sequence. If you started a job at $40,000 and you get a 5% pay raise every year, we could write down this sequence. You start at $40,000. After 1 year, if you remember how exponentials work, after 1 year, you'll be earning 5% more. The quick way to get 5% more is to multiply times 1.05. So you notice the second salary, whatever that happens to be, I'm not calculating because I want to see the pattern, but this second salary is going to be 5% more than the first salary. And if it happens every single year, well then the next year is going to be 1.05 times the previous year. Well, if you take this previous year times another 1.05, then that will become 1.05 squared. And I think maybe you can start to see what the pattern becomes here. If you keep this going every year, you're going to be getting higher and higher powers of 1.05. And so this becomes what we will call a geometric sequence. A geometric sequence is a sequence where each term is a constant multiple of the previous term. Or if you'd like another way to say it, the ratio of successive terms should be constant. Last time it was the difference. For arithmetic, it's the difference between two consecutive terms is constant. Now it's the ratio, or the division of two consecutive terms that is the same every single time. So when we're finding the nth term of a geometric sequence, the nth term is always going to be, you may notice the pattern, you still have that first term in the one with the salaries here, you still have $40,000. That was the initial salary, and that's in every single term. So we still have the first term, but then we have the common ratio, which is 1.05, raised to some power. So once again, we have to see what the power is. The first term had no powers. The second term had 1 power of 1.05. The third term had 2 powers. The fourth term had 3 powers. So maybe you can catch that the powers are always 1 less than the term number. Very similar to our formula for arithmetic. You have an n-1 involved with that. So that's going to be our formula for finding the nth term of a geometric. We also need to be able to identify whether they're geometric or not. And so the quick way to figure out whether they're geometric is to figure out what the common ratio is. And the best way to do that is to divide that way. So take the next term and divide by the previous term, and that will give you your common ratio. So for the first 2 terms, the common ratio would be 5. For the second 2 terms, if you take 125 divided by 5, that gives you 5. Sorry, it's not 125, it's just 25. Oh, I know what I did. It's 125 divided by 25, which is 5. That's the same common ratio. So far so good. We have the same common ratio. It just has to work one more time. So if we take the fourth term divided by the third term, if that's 5, then we have a winner, and we do. So if you divide right to left, right to left, right to left, and you get the same exact number every time, then that's a big old yes, because there's a common ratio. The common ratio is 5 every single time. That makes it geometric. All right, so do the same thing with here. take the next term divided by the previous term, next term divided by the previous term, next term divided by the previous term. And if you do that every single time, you'll find out that there is a common ratio and it's -1/2. So that also is a big yes. And finally, this one, if you do the common ratio, you find out it's 6/12, then it's 4/6, then it's 3/4, and those are not equal. So that's a no. There is no common ratio. So that's how you tell a geometric. So summarizing again, the nth term of a geometric sequence is always the first term times the common ratio raised to the n-1 powers, where a(1) is always the first term and r is the common ratio of consecutive terms. So if we're going to write a formula for that salary problem that we just did there, the nth term for the salary problem is going to be the initial salary, which was $40,000, times the common ratio. If they're getting a 5% raise every year, the common ratio is 1.05. And we always raise that to the n-1 power. So there's the formula. So if we do a question about what's the salary after 10 years, we also have to be careful again, because after 10 years means they're looking for the 11th term. Same sort of thing with the previous problem we did. So we are looking actually for the 11th term. That's what our salary will be after we've been there 10 years. So we calculate $40,000 times 1.05 raised to the 11 minus 1 power, which would be the 10th power. And I believe that then gives us 65,156. Hopefully that's right. I'm just following my notes. I didn't really calculate it live just now. But if we follow our pattern, that should be the correct answer. If it's not, we'll fix it later. And you might just notice this formula that we came up with does look like something, doesn't it? It's not linear. It looks exponential. And so geometric sequences and the formulas for them act like exponentials. When we have common ratios, that's going to be from an exponential function, an exponential pattern. So there you go. There's your introduction to both arithmetic and geometric sequences. Your homework is a little longer, mostly because it's just calculations like we just did. It's pretty quick and easy if you have the formulas. And you need that practice since this is something brand new. We used to teach this in Algebra 2, but apparently that has been dropped out. And so this may be actually your first time through learning about sequences and series. So good luck with that. Let me know if you have questions along the way, and I'll see you soon in class.